name is Nima, and I'm a team member of Royal Tire Content System. I work with William Sinani under supervision of Michael Nima and Professor Conrad, and I'm so thankful to them because of all their support during this project. Aim of the work is building a system which will count tires in different lighting conditions with most reliability, and at the same time it can install easily and uninstall easily, and with a quick set of time. And the last priority to make it as much as possible low cost. And because of that, we had a company visit. Well, at first, they took it as a university project, but then we realized that there's a serious industrial need in this section. And then we had a company because of that. And one of the companies which are working in this field and loading and unloading tires for import or export or working as a local distributor. At present, it's worth noting that at present, these companies are counting tires initially by their workforce and manually by their hand. And either they go for the secondary method, which is machine vision, or stick with the first method, which is the manual method. In the secondary method, they put tires on some conveyor belts and put some cameras on predefined places at very stable lighting, and they read the tire DOT, which consists of some letters and characters and numbers on tire sidewall. And based on that, they could recognize some more information related to tires, like manufacturer's name or some other information. And based on the shape of the tire, they could recognize and categorize the tire. The application area of this system is, it could be inside the warehouse or at loading and unloading sites. In loading and unloading sites, as you can see through the images on the right, they are mostly using two containers, one fully loaded with tires and the other which is empty, and they put the containers back to back and very close to each other. Some workers inside can roll the tires from the full container to the empty one, and some other workers will categorize the tires if there are more than one type of tire inside the container and count them. And our solution is somehow going to be used for this initial counting, but I will talk about it later at later slides. First, we focused on a fixed tire size, which in our case it was a 14-inch tire size, and the exact number, as you can see on the top left side of the screen, is 175, 70, or 14. And we designed the pattern which consists of 5 cells, as you can see through the image on the right. And there are 4 cells around, and these 4 cells are going to cover the edges of the tire. And because of that, we had to measure the dimensions of the tire and calculate how much is it. So we could put these cells apart from each other based on this calculation that you can see on the screen, on figure 3. And each cell indicates LDR, which is light dependent resistor. And there are 5 cells, which means there are 5 LDRs on one side, if you see through this image. And there are 5 lasers also on the other side, which each laser and each laser are placed exactly on the straight side of each other, so they could communicate with each other and interpret the signals when the tire is rolling through the scene. And I can show you here how the pattern works when a tire is passing in front of the cells. When they are getting the signal on the sidewall of the tire, the cells are becoming green. I play it again. This is the sensory schematic and the sensory block of the system that we could read the signal and send them to PLC through a microcontroller, which in our case we use an Arduino. And we could see the results on HMI, which we use the PLC screen to show the results. And the electronic schematic of our system consists of three main blocks, which is transmitter and receiver blocks on the left, power and amplifier block in the middle, and the logic block on the right. That the signals from the LDR side are going to pass through Arduino, and we use a driver chip to convert the somehow as an amplifier for powering, and we use some relays or switching to send the signals to the PLC. And we empowered the laser line using Arduino. This is the framework of our system. We used it as it was a concept work at first, so we built it using the aluminum frame that you can see through these images. And the placement of those lasers and LDRs, for example, this one is an LDR, we place it here, and the other one on top are lasers placed on the tire, and this is how these two frames are going to be placed in front of each other, and the tire is passing. Although the distance between these two frames is not at this far, but it could be up to 20 meters in our case. It depends on the laser and the laser that we are going to use. For our case, it could be up to 20 meters. And we are going to work on it to make it adjustable further. For the logic part, which is somehow the core part of our work, and it took a lot of time to develop it. Here we are calculating time and speed, and we used some countdown, up-down counter, or different types of relays like latching relay or wiping relay or pulse relays, and some pulse generators alongside all other logical gates, and some mathematical instruction also. Here we were detecting the direction of the tires and counting the tires in each direction. And it was somehow the most important part of the logic, that we were going to ensure that the object that is passing through the scene is the desired tire in our case. And we programmed the robots and solid detection in this part to distinguish our desired tire between the different objects, or even passing a human in front of the system. And also we were counting here the total number of tires. We designed two displays, or two screens for our project, for the HMI, and that could be switched between them by a physical button on the circuit. The screens on top, the green screens, are how it's designed in the program, in the software, and the white background screens on down are the matching ones from the top, and showing in real time taken from the PLC screen HMI. And I can tell you that here in this bar, we are showing total number of tires counted. Here we are showing the time that it took to pass the tire through the scene, the sweep here. And these two off and directions show the direction of the tire which is passing through the scene, and they become on when the tire is passing through the scene. And the second screen, we are showing the number of counted tires in each direction, and it's showing the direction. And here also. And but for to be more detailed, we were also measuring the time for half of the scene, for the tire that is going to pass for half of the scene, so we could detect some abnormalities in tire detection. So be more accurate. Here is a movie I will play for you for the reliability test of our system. You can see here the screen, which is now 0 counted. And someone is passing in front of the system. It says still 0, as you can see here. Still 0. You can see counted the tire. And here the direction also on the second screen. Here 0 and the other one was 1. And the top contrast is 1. Still 1. And 2. We conducted the test in 3 rolling profiles as wobbling path and bumping and angular rolling, and for wobbling and angular rolling or direct rolling of the tires, the system could detect completely all the tires. For 40 rolls of the tire, it means 100% results. And although we had some problems in detecting the tires when they were going to jump in front of the system. So it means that the tire was not placed exactly in front of the cells. And we also conducted the test in the different lighting conditions in complete darkness, as much as possible to make it complete darkness, and also in room lighting, which as we measured, it was 1,000 lux. And the results we got were so satisfactory as 100% for different rolling profiles. And the direction detection also, as we measured for 80 times, it was completely true and 100%. And the system is completely low powered system, which the total consumption is 1.655 watts. And the data of the counting also could be accessible through the PLC log, which is going to be saved in CSV format. And as you can see here on the table, and it's showing the number and also the timing of the countings and rolling of the tire and the other details that we were defining for the system to work. As a conclusion, our system, we can make some advantages and disadvantages for it. The advantages, I can count the robustness in industrial condition and low power system, easy to install and portable, which is a very important for companies and less sensitive to light fluctuation compared to machine vision system. And disadvantage is the inability to retire DOT and the inability to meter tires at the moment. But we have the plans for the future were to expand the supported tire sizes, and so measuring the tires and detecting the tire sizes. And also we are able to add external screen or somehow providing the details on a remote connection and running a web server for it. And adding some light resistant pipes as a cap for each LDR. So in this case, we are limiting the effect of the external light on our LDRs, and also we can add some convex lenses inside those caps. So by using this way, we can ensure that the emitted light is received on LDR side. Or we can use one housing transmitter and receiver which are packed in one unit. Thank you for listening.
Okay.
And I'm ready to.
Question? Any question? Very good. Okay, my question is actually I know that one is a real experiment, and you are using a small PLC.
Yes.
But actually, we don't need that kind of PLC. We need actually very accuracy, but very cheap, maybe within some dozen euro, even everything. With a microcontroller, very small one, and you can do it one with almost 100% accuracy. Count up, count down, you know that one. I think I strongly that the accuracy 100%. Because you count down, count up, in that one, if you have a good pattern, very fast one, very fast, and no problem. So that is my comment. My question is the reason you see that one is the direction movement, the accuracy only 60 or 80%, right? So why? Yeah,
Here, you.
Direction here also 100%, right?
Yeah. The accuracy of counting tires for direct rolling and angular rolling and wobbling of the tires was 100%. But in case that the tire was jumping in front of the system, since our system is going to be content based on interpreting the signals from a laser sight, and the laser sight, some of them with the down lasers, the lasers that are placed on the down side, are not going to be, well, the LDR are not going to be sensed by the tire, since the tire is jumping in front of the set, and that the LDR is going to be omitted. That's why the signal, the system has an error in counting the tire, because the pattern is not going to follow. But regarding the cost of the system, it's worth noting that compared to machine vision system, it's a lot cheaper, and the final cost of this system, as we have evaluated, is around or less than 500 euros. And well, our future work and next plan is that I'm already working on it, is counting the maximum number of tires, which is around more than 600 different tire sizes and tire types, and it's going to be done completely. Well, I'm doing my best to make the detection completely 100% and still reduce the final cost of the system. And well, the advantage of that, the next version or this one is going to also make it even more portable and easier to be installed.
So that system, the cost is how much?
You can count on less than 500 euros.
500 euros. Because my opinion, my comment is only if you use a very small microcontroller, you can do everything. Oh, and you can see the controller backward because you count only 1, 2, 3. Okay, that. Okay, yeah. Here you see the count here is not professional because people want to see the count up, count down, reset everything. You can see everything for if you design the console or controller. You see that one and reset and store and everything function there.